like to welcome you all to this second day of the Quantum Week of Fun. Today is the day of quantum algorithms. Welcome to this bright sunny day here in Cambridge. And the first speaker of our day today is Laura Mančinska from the University of Copenhagen. And well, Laura's been at the University of Copenhagen about 3 years now, I suppose, having previously done a PhD at the University of Waterloo in Canada and a couple of different postdoc positions. But today she's going to be telling us about what I think is some really exciting work relating quantum isomorphism to homomorphism counts from planar graphs. So Laura, over to you. Well, before actually I hand over to you, I should say to all of you watching on YouTube, if you have questions, you can post them at any time on the Slack channel for this talk, and I will get to them at the end of the talk, and I will read them out to Laura. So please do post questions, comments, any discussion on the Slack channel. With that, it's over to you, Laura.
Thank you for the very nice introduction, and it's my pleasure to have this opportunity to talk to you. And so I want to tell you about this class of non-local games or interactive protocols that I'm going to refer to as quantum isomorphisms, and in particular, how we can think of them in purely combinatorial terms, specifically in terms of counting certain objects. So in this talk, I will show you results from a few different works with different sets of co-authors. So in the very first one, chronologically on the bottom here, we introduced this notion of quantum isomorphism via a specific non-local game. And I will go through that later on. Then in a follow-up work with Martino and David, we established this connection of quantum isomorphisms to this area of quantum groups, which is really quite abstract area of mathematics, specifically non-commutative mathematics. And finally, in this talk, I will want to focus on this combinatorial characterization of quantum isomorphism, so how we can understand these quantum strategies for this non-local game in terms of combinatorics. And in order to do so, this link to quantum groups will actually be crucial. All right, so I really see quantum isomorphism as lying between these three different areas. First, its definition comes from quantum information through these non-local games. And then, as I said, we have this reformulation that only uses objects that are studied within this area of quantum groups. And then finally, we also have a combinatorial way of thinking about these quantum isomorphisms. All right, and why am I interested in this class of games? Let me tell you my perspective, kind of the bigger picture. Well, in general, I think of non-local games as providing us a way to study entanglement and kind of the advantage that entanglement can bring in some distributed scenarios where you have some distributed parties and you want to know what can they do using entanglement that they wouldn't be able to do with just classical technologies. Now, in this framework of non-local games, we can kind of try to go beyond just having examples, scattered examples maybe of protocols with this quantum advantage, and try to understand how big this advantage can be, what is the general behavior of these entanglement-assisted strategies, and so on. So kind of perform a more systematic study and develop a broader understanding. Okay, but now that's all very nice, but then there's a problem. Namely, if you just look at an arbitrary non-local game and want to consider its entanglement-assisted strategies, then they are often very unwieldy, sort of mathematically hard to understand. They seem to lack some additional structure that would give you a good handle on them. Right? And then one way around it is to sort of, instead of looking at arbitrary non-local games, is to focus on some class of games where their entanglement-assisted strategies possess some nice additional mathematical structure, which then allows you to make meaningful statements. about it. And of course, you want this class to sort of be rich enough so that it still exhibits some interesting properties of entanglement that you want to look at. And maybe this importance of such nice classes of non-local games is really underlined by relatively recent Lovasz breakthrough results, where, among other things, he showed, for instance, that the quantum correlation set is not closed. And we had this as an open question for quite some time. And the reason why he was able to resolve it is because he focused on this nice class of games, namely linear constraint system games. And the additional structure that they possess is that of an underlying group. In case of quantum isomorphisms, our underlying mathematical structure is that of a quantum group, which is a more general object than just a group. Okay, so that's kind of the motivation for these games for me personally. Okay, here's my talk outline. I will start I roughly think that this talk is split into 3 parts. In the first part, I will introduce this notion of quantum isomorphism and go over certain ways of how we can think about it in from different perspectives. Now, in the second part, I will present this combinatorial characterization and discuss its implication and how it fits into the context of other similar counting complexity problems. And in the very last part, I will try to show you a glimpse into the proof. I'll just focus on some kind of small, on some ingredients in the proof that I think are maybe particularly interesting to me, at least. Okay, so let's start with introducing this quantum isomorphism. So let's start from the very basics. So graph isomorphism. So intuitively, this is trying to capture the notion that 2 graphs are the same. But maybe we have labeled the vertices differently, so it's not obvious to us at first that it's the same graph. Here's an example. You can probably all see that these are indeed the same graphs. Now, when the graphs become bigger, it's of course not so easy. Now, more formally, we speak about an isomorphism map. And this mapping takes vertices of one graph to those of the other. And we require that this map is a bijection and that it preserves the structure of our graph. Namely, if we take two adjacent vertices of G, then f of G is adjacent to f prime of G. And also the same holds for non-adjacency. So this mapping F, it needs to preserve adjacency and non-adjacency relation. And here I'm using this tilde symbol to denote adjacency. Right, and whenever such a map exists, we will say that the graphs are isomorphic, and I'm going to write it using this congruence symbol. Now, there's an alternative way of thinking about graph isomorphism in terms of the adjacency matrices of the 2 graphs. Now, adjacency matrix encodes your graph. It's a 0-1 matrix, and its rows and columns are indexed by the vertices in your graph, and then you place 1 in the entries that correspond to adjacent vertices. And then we say that 2 graphs are isomorphic if we can find a permutation matrix that conjugates the adjacency matrix of one graph to that of the other. Or alternatively, we can write it in this form, sort of that it commutes through and gives you the other adjacency matrix. Okay. Now, to get started with quantum isomorphism, we need yet another way to think about isomorphism, and that is going to be in terms of this interactive protocol or non-local game. The way you should think about this game is that we have 2 players, Alice and Bob, and they are trying to convince this verifier or referee that the 2 graphs are really the same. This game is going to proceed as follows. So the referee selects 2 vertices of G. He sends G to Alice and G prime to Bob. And now Alice and Bob, without communicating between themselves, they need to respond with 2 vertices of H. So they reply with H and H prime respectively. Now, in order to win, what we want is that the relationship between the input vertices, so these 2 vertices G and G prime, is the same as their answer or output vertices h and h prime. And what is this relationship? If you take two vertices of a graph, then they can be related in one out of three different ways. First, they could be the same, or they could be adjacent, or they could be distinct non-adjacent. Okay, so for instance, if Alice and Bob receive adjacent vertices g and g prime, then in order to win, they need to respond with adjacent vertices in h and h prime. Okay. All right, now, okay, and so after Alice and Bob receive this g and g prime, they cannot talk to each other, but they could agree on some strategy before the game starts, before they receive these g and g prime. So they know the two graphs g and h ahead of time. They could agree on some strategy. Now, it's indeed not hard to observe that Alice and Bob can win this game with success probability 1. So when I'm going to say win, I will always mean with success probability 1, or irrespective of these received vertices g and g prime, if and only if the graphs are isomorphic. So one direction, both directions are rather easy, one direction is really trivial. So if the two graphs are isomorphic, then you have this mapping F that takes the vertices of G to those of H, this isomorphism map. And then the player could simply respond with F of G or F of G prime. And because this F preserves the structure of the graph, this relationship between the input vertices will be maintained. And then you can also go the other way around. Whenever you have a winning classical strategy, you can extract this isomorphism map F from it. Okay, so we can prove this statement that a winning classical strategy corresponds to isomorphism. And therefore, we could define quantum isomorphism as simply existence of a winning quantum strategy. So we will say that two graphs are quantum isomorphic precisely when there exists a quantum strategy that can win this game irrespective of these vertices g and g prime that the referee selected. And in particular, we focus on this class of quantum commuting strategies. And I will now explain what a quantum commuting strategy is. It is slightly more general framework of modeling composite quantum systems than the tensor product model that we are used to. All right. So in a quantum strategy, Alice and Bob can share some quantum state psi. And then upon receiving the input, Alice can choose which measurement she will do. And without loss of generality, we can index the measurement outcomes using vertices of our target graph H. So for every vertex pair G and H, we will have some measurement operator. And similarly, Bob can decide what measurement he will do whenever he receives some input vertex G prime. Right? Because we are in this commuting model, the shared quantum state psi is modeled as a unit vector in a Hilbert space H that is not necessarily a tensor product. Okay? And in particular, it could also be infinite dimensional. And now these measurement operators, these EGH, they will be positive operators on the Hilbert space, and they will add up to identity, and the same for Bob. And now this requirement that Alice and Bob are separate parties, that is captured in this condition that Alice and Bob's operators must commute. Okay, notice if you were in this tensor product model, then actually Alice would act on one space and with identity on Bob's space. And so these operators would necessarily commute because they would act non-trivially on separate spaces. Okay, and now if the players use this strategy described by this state psi and these measurement operators, E's and F's, then the probability that upon measuring with measurements G and G prime, they respond with vertices H and H prime is given by this inner product. Notice how you're probably used to seeing a tensor product here, but because we are in this commuting model, then it's simply the product of these two operators here. All right, and now if our two graphs are quantum isomorphic, that means that we can find the state psi and operators these E's and F's, such that this inner product is 0 whenever this corresponds to a losing question-answer pair, because we must be winning with success probability 1, so we lose with probability 0. Okay. So this is how a quantum isomorphism is defined, as the existence of this winning quantum strategy for this interactive protocol. Now, it turns out that we can think about this strategy in the language of these quantum groups. And specifically, we will need to use this object called quantum permutation matrix, or sometimes people also call it magic unitary. You should think of it as a generalization of a permutation matrix. Now, in a permutation matrix, your matrix entries are 0 or 1, and along every row and column, they add up to 1. Now, in case of quantum permutation matrix, the entries now come from some C-star algebra. So in particular, they could be matrices themselves. And this requirement of being 0 or 1 is replaced by asking that these entries, they square to themselves and they are self-adjoint, which of course holds for numbers 0 and 1. And then we also require that if we sum these entries along every row or every column, we get a 1. But now in this case, 1 is the identity element in our C-star algebra. Okay. And now with this quantum permutation matrix in hand, we can characterize the quantum isomorphism as follows. We can say that two graphs are quantum isomorphic if and only if there exists a quantum permutation matrix U that conjugates the adjacency matrix of one graph to that of the other. And notice how this is really similar to this adjacency matrix definition of usual isomorphism. It's just that we are replacing permutation matrix P with now a quantum permutation matrix U. Right? Otherwise, this equation syntactically looks exactly the same. Okay, so now I want to finish this kind of first part where I give you an overview of what this quantum isomorphism is and some related things by showing you an example of two graphs that are not isomorphic, but that are quantum isomorphic. Okay, so here are the two graphs. This is actually the smallest example that we know of, and these graphs have 24 vertices each. And the way we obtain is actually based on a more general construction, which uses a reduction from this class of linear system games. And the underlying linear system game for these two graphs is the so-called magic square game. All right. Okay. So in the next part, I want to talk about this combinatorial characterization. So we can now sort of understand what does this quantum isomorphism mean from the perspective of quantum information or even from the perspective of quantum groups. However, if you want to explain what does it mean for two graphs to be quantum isomorphic to a classical graph theorist, then it's not so easy because we don't have a combinatorial way. We must invoke these quantum strategies, which people are often not comfortable with. All right. So now in this part, I'm going to be going towards presenting this result of combinatorial characterization. And this characterization is going to be in terms of counting graph homomorphisms. So a graph homomorphism from F to G is a mapping that takes vertices of F to those of G, and it must preserve adjacency. So whenever I take two adjacent vertices, U and V, their images must also be adjacent. Okay. But for non-adjacent vertices, I have a choice. I can do whatever I want. Here's an example. So we can take a 7 cycle and map it using a graph homomorphism to a 5 cycle. by essentially identifying these blue vertices and these red vertices into a single vertex in the 5 cycle. And if you want to think about these graph homomorphisms pictorially, then essentially you are taking the vertices of your source graph, you're placing them onto the vertices of your target graph, and you want to do it in a way so that every edge in your source graph lies above an edge of your target graph. Okay. Now we might not only be interested of whether a homomorphism exists from one graph to another, but how many homomorphisms are there? This quantity is usually denoted using the symbol hom of f comma g. So it is the number of homomorphisms from graph f to graph g. And it turns out that there is a relationship between these homomorphism counts and isomorphisms. And this was established in a classic result by Lovasz, who showed that actually these homomorphism counts, they determine a graph. Okay, namely 2 graphs G and H, they are the same precisely when they have the same number of homomorphisms from any plane, any graph F. Okay, so one direction is obvious. If your 2 graphs are the same, then of course, no matter what graph F you take, it's going to have the same number of homomorphisms into G and into H. But to get the other direction, you need to do some work, but it is not very complicated. All right. And then we were actually very surprised to find out that a similar characterization can be also obtained for this quantum isomorphism, right? Namely, we can get that 2 graphs are quantum isomorphic precisely if they have the same number of homomorphisms from any planar graph F, right? In case of isomorphism, we look at homomorphisms from all graphs. In case of quantum isomorphism, we restrict to planar graphs, right? Okay. So now one surprising corollary of this theorem is that determining whether there exists a planar graph F that admits a different number of homomorphisms into G as opposed to H is an undecidable problem. The reason why it's surprising is because usually planar graphs is kind of like a nice class of graphs to work with. Usually you get more efficient algorithms and so on. But here we get an undecidability result. And as we will see on the next slide, actually, if you pick other classes of graphs, you get efficiently computable relations on graphs. So let's now try to put this into context. So let's see what happens if we restrict the class of graphs from which we are counting these homomorphisms. What kind of results are out there? So for instance, if instead of all graphs, we focus on only cycles, then the relation of graphs that we obtain is cospectrality. Right now, there is also this commonly studied relaxation of isomorphism known as fractional isomorphism, where you are requiring that there exists a doubly stochastic matrix. So that means a matrix with non-negative entries such that along every column and every row, the entries add up to 1. It's kind of like the convex hull of permutation matrices. So you are asking that there exists this matrix D such that the adjacency matrix of G times D is equal to D times the adjacency matrix of H. And then you say that the 2 graphs are fractionally isomorphic. So now this fractional isomorphism, it can be expressed in terms of homomorphism counting, where you look where your source graphs are trees. And then this result was obtained by Dvorak back in 2010, but then later on it was reproved in this very recent result by Delcroix and Rattan. And that's where we learned about this result. Right, and actually, even if you take this relaxation of fractional isomorphism known as k-dimensional bispiral lemon equivalents, then that can also be expressed in terms of counting homomorphisms. But now you need to look at all graphs with tree width of at most k. And all these things, they are efficiently computable. So co-spectrality, fractional isomorphism, and also k-dimensional Weisfeiler Lemon equivalents. And actually, in this paper where they obtain these results, Dale, Groh, and Rattan, they ask what relation on graphs would be obtained if we consider the class of planar graphs, and what would be the complexity of testing this relation. And of course, they didn't think that the complexity could go as high as undecidable for such nice class as planar graphs, but it turns out to be the case. Okay, and finally, I want to show you one more consequence of this combinatorial characterization. And that is that it gives us a certificate of a quantum non-isomorphism. So if two graphs are quantum isomorphic, then there is sort of a natural certificate that we can think of certifying this quantum isomorphism, namely this quantum strategy. Now, I want to caution you that it is not a certificate in kind of usual complexity theoretic sense, because the certificate is not efficiently specifiable, and it might not even be finitely specifiable, because these quantum strategies might be infinite. And now still, you have this object, this quantum strategy, kind of proves that the two graphs are quantum isomorphic. But how do you show that two graphs are not quantum isomorphic? How do you show that there does not exist a quantum strategy? And in one of our previous works, for instance, we wanted to show that these two graphs, this root graph and Shirkundi graph, that they are not quantum isomorphic. And we needed to use quite a lengthy argument. But now that we have this combinatorial characterization, we know that there is always this certificate of non-isomorphism in terms of a planar graph that has a different number of homomorphisms into one graph as opposed to the other. So in this case, this planar graph that we could use is K4, so complete graph on 4 vertices. This graph is planar. Now, counting the number of homomorphisms simply of K4 into a graph simply corresponds to counting the number of K4 subgraphs. Now, we easily see that in this root graph, there are many K4s. Like if you look at any row or column of vertices, that is going to give you a K4. But now, in contrast, the Shirkundi graph does not contain K4 at all. So the number of homomorphisms for the root graph is going to be greater than 0, but for Shirkundi graph is going to be 0. And because it's not the same number, then we know that they cannot be quantum isomorphic. All right. So now this concludes kind of the second part of my talk, where I wanted to explain you the result itself and the context of the result. And in the final part, I want to go through some proof ingredients. Are there any questions at this point? Because now I'm going to kind of switch gears a bit.
Yes, Laura, there have been a couple of questions on Slack. So maybe if you could go back a few slides to the definition of quantum isomorphism on slide 9, it was. Yeah, no, the next one, the next slide. Right. So one question was, with these adjacency matrices AG and AH now of the two graphs, presumably the entries are 0 and 1, where 1 is the identity, of the C-star algebra.
Yes, so very attentive listeners. Yes, so you could ask, oh, how do we multiply these matrices together, right? They don't seem to have the same type, sort of, if I think of in terms of scalars. But indeed, like one way is to think that the 0 is kind of the scalar 0 times the identity matrix of your algebra, and 1 is 1 times the identity matrix of the algebra. And then you kind of multiply like you intuitively would multiply these matrices together.
And a related question. So you say for some quantum permutation matrix, so presumably this means for some C-star algebra. If you fix one particular algebra, you get a different notion. In some sense, for any fixed C-star algebra, you have a different notion of equivalence here.
Yes, so you would say, yeah, it's just for some C-star algebra, you're right.
So that in some sense, that's where the undecidability comes from, because you can't, if you had a fixed C-star algebra, that presumably this would be decidable.
Yes, yeah. Well,
or if it was a finite, yes.
Yeah, I don't know, maybe there is some kind of complicated C-star algebra over which it would still not be decidable. Yeah, but for instance, you could just take the C-star algebra of just some numbers, right? A commuting one. So then it would reduce to the usual notion.
And can you give us some idea why it is undecidable?
Essentially, like one way to think about it, maybe the easiest one, right? You could kind of think that all these entries are matrices. Maybe your C-star algebra is the matrix algebra, right? And then these matrices could be of arbitrary size, right? Then essentially you need to look at matrices of size that can go to infinity. Like when you have undecidability result, you have something that can go to infinity. Otherwise, you can look through all the possibilities.
That's right. That's right. So which is why fixing the algebra in advance, especially if it's a finite algebra, would give you decidability.
Yes. Yeah. Exactly.
Okay. So thank you for the questions. I should say these were questions from John van der Wettering and Alec Edgington on Slack. And now I think we'll let you carry on to the third part of your talk, Laura.
Yeah. Okay. Yeah. Thank you. Very good question. All right, so now I want to give you some idea about the proof. So how do we relate these two things, like these quantum strategies on one hand, and these counting homomorphisms on the other hand? And our path is going to go through these quantum groups, right? So I will try to briefly introduce those. And specifically, we will look at quantum automorphism group of a graph. Let's first start by looking at the classical notion. So an automorphism is just isomorphism onto itself, right? So again, we have this mapping, but now we're mapping vertices of graph to themselves, and we want this to be a bijection and preserve the structure of the graph. So for instance, if I have a 5 cycle, and then this map where I map every vertex to the next one, kind of like rotate this cycle, then this would be an automorphism of this 5 cycle. I could also reflect, and that would also give me an automorphism. Okay, now these automorphisms, I can perform them one after another. I can compose them, and they form a group with this operation of composition. And that's called automorphism group of a graph, denoted by aut of G. And just like in case of isomorphism, we also have this matrix-based definition or way of thinking about automorphisms. So in terms of existence of a permutation matrix, which now conjugates the adjacency matrix to itself, or in other words, it commutes with this adjacency matrix. All right, so now let's try to go to quantum groups. And now I'll try to give you a very kind of intuitive, hand-wavy explanation of how these quantum groups arise. So there is a one-to-one correspondence between compact groups and certain C-star algebras, which are commutative. In particular, we are looking at the algebra of functions on your group. Okay, so there's this one-to-one correspondence in this case. Then what you could do is you could take this commutative C-star algebra, usually just expressed in terms of generators with some relations, and all of these generators are commuting with each other, and now you drop this commuting requirement. Now you will get some potentially non-commutative C-star algebra, and then you think that the underlying object behind this non-commutative C-star algebra is now a quantum group. And a quantum group is not a group, it's sort of a virtual object. The thing that actually exists is this algebra. Okay, so I'm by no means an expert on quantum groups. This is my outsider understanding of what these quantum groups are. All right, but we will be looking at the specific type of quantum groups, namely quantum automorphism groups of graphs, and we will denote them using QUT of G. They were defined by Panica. So now, remember I said that the thing you should think about quantum group is that there's this algebra. Now, this algebra is generated by the entries in your quantum permutation matrix, U, and the requirement is that this permutation matrix, it commutes with your adjacency matrix of your graph. All right, and then the quantum automorphism group is given by this algebra together with this co-multiplication map. All right, so we have this algebra and we have this quantum permutation matrix U that commutes with our adjacency matrix. And this U is often called the fundamental representation of the quantum automorphism group. Now, the thing that we really need from these quantum automorphism groups is going to be the things called intertwiners. And they are defined in terms of this fundamental representation U and its tensor powers. Okay. Now, for every natural number, pair of natural numbers L and K, we can talk about LK intertwiners of our quantum automorphism group. And these intertwiners, they are going to be matrices of size n to the L by n to the K, where n is the number of vertices in your graph. And they are now simply made, the entries in these intertwiners, they are simply complex numbers. So no C-star algebras in the intertwiners themselves. Okay? They are usual matrices. But they need to satisfy this relation with respect to this fundamental representation U. Okay, so that you should be able to pull through this L tensor power of U through this intertwiner on the other side. And again, we do this multiplication in a similar way like we discussed before. Okay, where we think that every entry is kind of that scalar times the identity element of the algebra to make sense of that multiplication. Okay. Now, this is an LK intertwiner. So these are matrices of varying size. Remember, the size was n to the L by n to the K. And then we could simply throw them all together, and then this is the set of all intertwiners. So we take union over all LK. And we can perform certain operations on these intertwiners as long as the matrix dimensions are such that we can perform these operations. For instance, we can take two intertwiners and multiply them together as matrices, and that will give us a new intertwiner, as long as we can, the dimensions make sense, so we can multiply. We can take tensor product, or we can take conjugate transpose, or we can take linear combinations of the same size matrices. And that will not, we will not leave this set of intertwiners for quantum automorphism. Okay, and here are three kind of important examples of intertwiners. The first one is the 1-1 intertwiner. So, and that is the adjacency matrix of our graph. So any 1-1 intertwiner would need to satisfy this relation. It needs to commute with this fundamental representation U. And remember, kind of the way we define this fundamental representation U was that it needed to commute with the adjacency matrix. So somehow this adjacency matrix, by definition of U, is a 1-1 intertwiner. Okay. And it can also be shown that the following two matrices are intertwiners. I'm not going to go through the details of how you do that. So This one is a 1-2 intertwiner, and I define this matrix by its action on the standard basis. So if you apply it to ith standard basis vector tensor, the jth one, then you either get 0 if I and j were different, or you get ei if this I and j were the same. And sometimes this is called multiplication map. Right, and then you also have a 1-0 intertwiner, which is simply the all ones vector. Sometimes it's referred to as unit. That's why I'm calling it U here. And the reason this is an intertwiner is essentially because along every row, the entries in your magic unitary, they are adding up to the algebra identity. Okay, so these are 3 important intertwiners, and there's a very nice theorem by Chassagnol that says that actually we can see any intertwiner as being generated from these 3 very simple ones using a set of operations. And these operations are linear combinations and then matrix multiplication, whenever we can multiply the matrices, or tensor product, and then complex conjugate transpose. So we can obtain arbitrary intertwiner just starting from these 3 very simple ingredients: this unit, so this vector of all ones, then this multiplication matrix, and the adjacency matrix of our graph. Okay, so now the part of the proof that I want to actually explain is how we can think about these intertwiners in purely combinatorial terms. And to do so, we look at these bilabeled graphs. Okay, so what is a bilabeled graph? It's a triple. So the first element f is simply a graph, and then we have some special vertices in our graph. We have some number L of output vertices, and they are ordered, so we can talk about the first output or the second output and so on, and the input vertices, and we have k of them. That's why we have an LK bilabeled graph. Okay, so here's an example. Here the graph itself is the complete graph on 4 vertices, and then we have 2 outputs. The first output is vertex 1, the second is vertex 2, and we have 2 inputs, and both of the inputs correspond to the second vertex in our K4. Right. Now, it's often very convenient to think about graphs in terms of pictures, in terms of actual drawings. And that's also true for these bilabeled graphs. I think we'll understand them much better once I draw a picture. All right, so how do we draw a bilabeled graph? And let's take a look at this example that we had before. So we have K4. So at first we just draw the K4 itself, and then we somehow need to indicate these inputs and outputs. So our outputs were vertices 1 and 2. And these input and output vertices, we indicate them using these thinner wires. Right? And I want that all of my inputs are on the right and all of my outputs come out on the left. And the reason we're doing that is, as opposed to the other way around, like you would do for circuits, is because I want to think of this as matrix multiplication. And then you multiply your inputs for a matrix come on the right and outputs come out on the left. Right? And I need to draw these wires so that kind of my first input comes out on top, my second is the second one, and so on. And then I join this wire to the corresponding vertex. Any questions so far? Okay. I'm assuming that it's more or less clear about these graphs. Now, yeah.
No, I think there are some questions on the Slack channel, but I think they're not. We'll come to those at the end. They're not.
Okay.
Yep.
Okay. All right, so let me show you 3 more bilabeled graphs, or drawings of these bilabeled graphs. And notice how I have chosen to call these graphs U, M, and A, and it corresponds to these 3 intertwiners that we saw before. And later, and I chose these names on purpose because there will be a relationship between these bilabeled graphs, U, M, and A, and the intertwiners, matrices, U, M, and A. Okay, so for instance, if we let's take a look at this bilabeled graph A. So the underlying graph is a complete graph on 2 vertices, and it has 1 input, which is, say, the second vertex, and 1 output, which is the first vertex. All right, but now we need to get this connection, right, between these bilabeled graphs and these intertwiners, which were matrices. So out of these bilabeled graphs, I now want to get a matrix somehow. The way we do it is by counting homomorphisms, or through what I'm going to refer to as homomorphism counting matrices. So here, let's take a look at an n-vertex graph G, and then a bilabeled graph F. And for simplicity, for now, let's assume that it has only 1 input vertex and 1 output vertex. Right? Then this homomorphism counting matrix of F. So I'm thinking of this graph, underlying graph G, as kind of being fixed, and I'm going to change these bilabeled graphs F. So the homomorphism matrix of F is going to be an n by n matrix, and overall, this matrix is going to count the number of homomorphisms from F to G. But I'm going to split these homomorphisms according to the images of my input vertex B and output vertex A. So I split the total number according to the images of these input and output vertices. Okay, so specifically, the UV entry, so and U and V are vertices of my graph G, is given by the number of homomorphisms from F to G, such that the output vertex A gets mapped to U and the input vertex B gets mapped to V. All right, let's see an example. So here, my bilabeled graph is one of these 3 special graphs that we saw before. It's this A graph. So the underlying graph is K2. I have 1 input, 1 output. Now let's try to understand what would be the homomorphism matrix of this A to some graph G. So the UV entry, right, it is the number of homomorphisms such that phi of the output vertex 1, so phi of 1 is equal to U, and phi of 2 is equal to V. Now, my graph K2 only has 2 vertices, so this actually fully specifies the map phi, right? I know that 1 goes to U and 2 goes to V. So all I need to decide whether this phi, whether it is a graph homomorphism or not. And the requirement for graph homomorphism was that I preserve adjacency. So I need to ensure that for this phi to be a homomorphism, that U and V are adjacent, because vertices 1 and 2 are adjacent. Okay, so then I see that this UV entry of this matrix is going to be 1 precisely when my 2 vertices U and V are adjacent. Okay, and of course, what is this matrix? This is just the adjacency matrix of my graph. Okay, so now I see that by choosing my bilabeled graph to be this A arrow, I get, as its homomorphism counting matrix, I get the adjacency matrix of my graph G. All right, now this was the definition kind of for the simpler case when you have only 1 input and 1 output, but we could write a definition for more general bilabeled graphs with L outputs and K inputs. Okay, and again, this matrix, all that it's going to do is going to count the number of all homomorphisms from from your graph F to G, but it's going to split them according to the images of the input and output vertices. So we require that the jth output vertex is mapped to uj, and the ith input vertex is mapped to vi, and that's going to give us this entry of the matrix. Okay, and of course the matrix size, because I'm indexing my matrix entries now by tuples of vertices of V, now my matrix is much bigger than before. Okay, and just like before, we saw that this homomorphism counting matrix for the bilabeled graph A gives the adjacency matrix. Similarly, we can see that for these bilabeled graphs U and M as homomorphism matrices, I get out now this vector U and the other intertwiner M in case of the graph M arrow. Okay, so now what we've seen, right, is that we can see these three special intertwiners, this adjacency matrix, U and M, as homomorphism counting matrices for specific bilabeled graphs. So we can go back to this theorem of Chassagnol's, which allowed us to see any intertwiner as being generated from these three simple matrices. And because we know that these matrices are homomorphism matrices, if I pick my bilabeled graphs correctly, then I can simply write it like in this manner. Because this matrix was equal to U, this to M, this to A. Very easy, once we have that correspondence. Okay, but now I still need to do kind of these algebraic operations to get all intertwiners. And what I want to do next is to understand how do these algebraic operations, say multiplication of these homomorphism matrices, how can I think of them as operations on graphs rather than operations on matrices? And it turns out that each one of these algebraic operations has an interpretation as an operation on graphs. So let's take a look at matrix multiplication. So in this case, the operation that I want to consider on my two bilabeled graphs is kind of serial composition, you could think. And the easiest way for me to explain it is actually show a picture. So now I have two bilabeled graphs, F1 and F2, and I want to compose them. In order to be able to do that, I need to make sure that the number of inputs of F1 is the same as the number of outputs of F2. But once that holds, what I'm doing is I'm just joining together the corresponding wires and then contracting them, which is going to end up in the identification of certain vertices. Okay, so for instance, if I look what's happening here, so I'm joining this, so I'm going to contract together this vertex A with 4 and also with the vertex C, and that's the vertex over here. Okay, and then the outputs of the resulting graph are given by the outputs of this graph F1, and the inputs of the resulting graph are given by the inputs of the bilabeled graph F2. Right, and then the theorem says that this multiplication of the homomorphism counting matrices corresponds to this composition operation on the two graphs. And so you can either multiply the matrices, but that's the same as performing now this graph operation on the two bilabeled graphs. And similarly, for the operations of tensor product of the two matrices and the adjoint as well. So for the tensor product, the operation that you do on graphs is pictorially, it would be taking the two graphs and just drawing one bilabeled graph above the other one. All right, so you will end up concatenating the inputs and the outputs. All right, and then the tensor product corresponds to doing this tensor product operation on the graphs. And in case of complex conjugate transpose, there what you need to do is you need to reverse, you need to swap your inputs and outputs. And in terms of the picture, you would just take and reflect your picture around a vertical axis. Okay. All right. So now, now that we know how to think about these algebraic operations combinatorially, we can try to understand what is the class of graphs that is being generated if we start from these three simple bilabeled graphs and then perform now these graph operations on them. All right. Now, to be fully precise, you need to introduce some additional notation, but what I'm going to do is try to give you an intuitive understanding of what this class of graphs is. So first, and I'm going to call it the planar bilabeled graphs. And these are bilabeled graphs where this underlying graph F itself is planar. But you also need to be able to draw these input and output wires without any crossings. So they cannot cross themselves, they cannot cross other wires, and they cannot cross edges in your graph as well. And you need to ensure that the first output wire comes out on top left, the second one, the second position, and so on. Right? So you need to ensure that this ordering is preserved. Okay. So the class of graphs that you get is these planar bilabeled graphs. Okay. And therefore, now we know that we can characterize these intertwiners of quantum automorphism group of a graph simply as the complex span of these homomorphism counting matrices, where the source bilabeled graph is an arbitrary planar bilabeled graph. And this gives you a combinatorial or counting complexity way of thinking about these intertwiners. And that's kind of a major ingredient in this proof. And I'm not going to go into the other details of the proof any further. All right. So let me just use one last minute to kind of summarize what we saw so far. So I introduced this notion of quantum isomorphism, and we did this through this interactive protocol or non-local game. And we said that quantum isomorphism is defined as the existence of a winning quantum strategy for this game. Right? And then we saw that on one way, we can think about the existence of this winning quantum strategy in terms of existence of this quantum permutation matrix U. And we also saw that there's a combinatorial way of thinking about these quantum isomorphisms, namely that two graphs, G and H, they are quantum isomorphic precisely when they have the same number of homomorphisms from any planar graph F. So that we see that this notion of quantum isomorphism, we can interpret it in 1 out of 3 different languages: in quantum information, in combinatorial counting way, or in the language of quantum groups. Thank you very much for your attention, and I'll be happy to take any questions.
Well, thank you very much, Laura. That was a really very nice presentation of some quite astounding results as well. Thank you. Now, if there are any questions to the audience out there, you can post them on the Slack channel. In the meanwhile, I'll pick up 1 or 2 things that people have been asking about. First, a little technical point about when you were talking about composition of bilabeled graphs. John van der Wettering was asking what happens to internal edges when vertices get fused. Like in your case, if there was an edge between A and C in this example, on the right-hand side, A and C become the single vertex. Do you get a self-loop on that vertex?
Yeah, so it's a very attentive question. Yeah, so we do need to take care of these edges, and I just didn't go into details. Essentially, we can forget about multiple edges because those could form, but we keep the loops. So this, and we would get a loop on that vertex. I'm just not drawing any edges in this graph. I'm only drawing wires.
Right. Okay, there were some further questions about the, a general question about the undecidability of this. So, I mean, we mentioned that because these C-star algebras, there's infinitely many possibilities to search for. The kind of obvious algorithm doesn't work, but that doesn't prove that it's undecidable.
Yes.
So I assume you have a proof of undecidability.
Yeah, so this undecidability result, it actually goes via a reduction. So we take an arbitrary linear system game and we reduce it to a problem about quantum isomorphism. So we show that this linear system game, it has winning strategy if and only if the corresponding pair of graphs are quantum isomorphic. And because we know that this linear system game,
so the linear decidability of that is due to
Slopster.
Slopster, right?
Yes, yes. Yeah. So we do it by reduction.
But I mean, I noticed another thing. So you, as you said, you have certificates for non-isomorphism by your result, namely a planar graph and its homomorphism count being different for two graphs, which means that non-isomorphism is semi-decidable.
Yes, yes.
And therefore it follows that isomorphism is not even semi-decidable, right?
Yes, yes, it's not. And it's precisely because this certificate is not finite. Like this quantum strategy, it might be infinite dimensional. So it's not finitely specifiable. Of course, otherwise you would get the decidability result. Yeah, exactly.
Okay. Okay. I'm having a quick look. There's a little bit of a discussion rather than a question on the Slack channel about the connection with open graphs in the context of ZX diagrams. Do you know anything about this?
No, unfortunately, I won't be able to weigh in meaningfully.
Right. Okay. Okay. I don't see any other questions there. Nothing new, but I think that was very, very nice. Thank you very much. And
thank you, guys.
Give you a round of applause on behalf of everybody. And there is, well, right now starting another talk on the second talk of the session starting on another channel. So we'll leave this here. Thank you very much.